Okay, let's begin our today's seminar. That will be the last seminar this semester. So in a week we'll have some kind of exam here, but at 6 o'clock. So now today's speaker is Alexander Shevchenko, who will present the results of his recent research made jointly with Arsenal Sokin on deep structured prediction models.
Quite long.
Yeah.
Thank you for introduction. Today I'm going to talk about our joint work with Arsenal Sokin on the subject of end-to-end training of deep structured models. First of all, I'd like to briefly recall the structured prediction setting. Like usual, we have a dataset of training pairs, xj, yj. The typical case here is that y have a structure. It means that yi, the indices of this structure, are highly correlated. The tasks of this type arise in many practical fields, such as computer vision and natural language processing. As examples, you may consider the sequence tagging, semantic segmentation, or human pulse estimation. The main question is how to encode structure in our model. One possible solution is to use the framework of energy-based models. In these terms, we are given with the score function, which scores the compatibility of assigning label y given x, using some potential functions. In these terms, the associated likelihood may be computed via softmax. And in this work, we are particularly interested in potentials up to degree 2. It's unary potentials, which measure the compatibility of assignment label yi to the input xi, and pairwise potentials, which scores pairwise assignment yi, yj. So now I'm going to briefly recall the training of such models. It's like a very typical setting. Consider the parameterizations of our potentials with theta. And the goal of training is to obtain the optimal configuration of the parameters, which minimize the average loss. Our loss function is depends on xj and yj, and the score function, which is parameterized by theta. A typical way to train such models is to use three-stage procedure, often two-stage. It consists of the following steps. First of all, we train the unary predictor on the unary potentials. Then we fix them and train pairwise potentials with possible simultaneous fine-tuning afterwards. This process works always if we were lucky to obtain like a good values of hyperparameters and tuned everything like in completely excellent way. But it's very time consuming, and it lacks of stability during the phase switches. The phase switching is just the changes of loss between the stages, because at first stage we have like a completely different loss, it's just the cross entropy for unary predictor, and at the second stage we have a structured loss, and we train on the pairwise terms, and at third stage we possibly fine-tune all end-to-end, and it's indeed different. And the very tricky part that we should consider separate hyperparameters for each stage. A quite natural way is to use joint training, like to train this system from the beginning simultaneously. It is completely faster because we need to tune hyperparameters like only once. There are less ambiguities, but however, this approach often unexpectedly fails due to increased optimization complexity, because now we're optimizing all the parameters. And we claim that the particular reason for joint training to fail is improper relative scaling of the parameters, namely the unary potentials and pairwise potentials. Are there any questions so far? Perhaps not. So as motivation, consider the optical character recognition case study. We have quite a simple model. It's linear chain CRF with unary potentials parameterized by a Lennard-like convolutional neural network, and pairwise potentials which are parameterized by real-valued square matrix of size 26. In this case, we can see from the table that the stage training is superior to the joint one. So let's consider the reparameterization of unary potentials. We just scale the factor, the unary potential, by some constant factor alpha.
And why the Unary potential doesn't depend on theta?
It actually depends. It should be theta here. Sorry. We have some nice plots. First plot shows the dependence of final accuracy on the scaling parameter alpha. And the key thing is here that the sweet spot is not contained in value of alpha which is equal to 1. The second plot shows the dynamics of ratio of unary to pairwise potentials. Ratio is computed like a fraction of mean absolute values of instances in unary potentials and pairwise potentials. We have three system architectures here. The ReLU with alpha equals 1, it's just like initial architecture. The sigmoid with alpha equal 1, it's slightly tweaked unary network. We have substituted the last pre-activation of, the activation before the last layer with sigmoid, not the ReLU. And this system lends itself to a joint training procedure and achieves comparable up-to-noise results with stage training. And we have another one with ReLU, but with the best possible choice of alpha.
And what is on the y-axis? Ratio of unary to pairwise? What do you mean?
I said that it's just the fraction of mean absolute value of instances in unary matrix and then pairwise matrix.
Why is it changed with the number of steps?
Because unary and pairwise potentials are learning. And so the dynamics are...
So the larger is the curve, the less is influence of pairwise potentials, right?
Yeah. The larger value, yes.
Yeah.
Okay, and we can see that both systems which lend itself for joint procedure, it's perhaps you don't see it, there is a green dotted line here. It lays quite close to sigmoid, which lends itself to joint training, and contrary to ReLU, which like diverges and have significantly bigger values.
But what conclusions can we make from this plot?
From this plot, just that the dynamics of ratio of both models which train simultaneously are like close enough. And the ReLU architecture which cannot be trained jointly, which can be trained jointly, but we achieve less effective performance, like have a significantly bigger values.
And see, it's not important that the value is bigger, that for other two architectures this ratio stabilizes, so within training it kind of gets constant towards the end. And for the blue curve it blows up.
Okay, then another question is about the left-hand plot. I think you mentioned about sweet plot, but as far as I see, joint training never helps in comparison to stage training, even for the best value of alpha.
No. Here's the stage training.
Yeah.
This here.
Yes.
Yes, and our joint training with good alpha, like here.
But
it directly coincides.
Yes, but it's not better.
It's not better, yes.
Although we could expect that, at least for the optimal value of alpha, it could be a bit better. No?
Yes, at least we could expect. But
yeah, but it's kind of, it's not clear why should it be better, because we are not increasing capacity of the model. So like this alpha parameter is just there, so it's kind of supposed to be invariant to this in some sense. If our optimization was perfect, it would be invariant. If our optimization was a fine invariant to like...
Yeah, but do you agree that joint training should be better than stage training?
Not necessarily.
At least it was claimed on the previous slide.
No.
It wasn't claimed, I just said that sometimes it is better. Sometimes.
But this is not the case.
But it is not the case.
Okay.
And also like one of the reasons, motivation at the beginning of this project, it was that literature, there is no consistent conclusion in the literature. Some papers claim that it's better, some papers claim that it's not. So it's like, it's not clear.
Yes, but if it's not clear, and you assume that stage training can achieve at least similar results, in stage training there's no such problem.
Yes,
but it's much harder.
But it's much
okay. A lot more hyperparameters.
Okay.
Why are ratios of unary to pairwise constant for real?
They are not constant.
With the best alpha.
With the best alpha, they're quite stable.
Here?
Yes.
On the right. Or,
On the right?
yeah.
Ah! I just didn't skip to it. Okay, it's just the stage training, the dynamics of stage training, the red curve. The horizontal lines denotes the final ratio. So this is the final ratio at the end of training.
After the both stages.
Yep, for the relo with alpha 1 and for the relo which we pick up the best. And the vertical lines denotes the phases. Here the first phase starts, here the second phase starts, and obviously here the third phase starts. And here it is ended. Okay?
So at the first phase we're tuning just unary potentials, right?
Yep.
Keeping pairwise potentials fixed, and then we fix unary potentials, start tuning pairwise potentials.
Yeah.
This is
And the key point is that on the first stage, unary potentials are trained like separately from pairwise, like on completely different objectives, just like in classical classification task, you have a cross entropy on unary and this all. And then you, on the third stage, you like add the pairwise potentials, and your loss is no longer not structured.
Yes, but I would assume that your loss function is still the same.
No,
Yes.
loss function is not the same between the first stage and the second stage.
The second stage, you still want to maximize the number of correctly recognized symbols.
Yes, but you have a score function there in your loss function. Okay, let me clearly explain it. At the first stage, you have like a completely ordinary classificator, and your unary potentials is just a logits. On the second stage, you like add up a new model, this pairwise term, and your new loss function, assume that you have some graphical model, you like do marginal inference in it, and you just pass these marginals in cross entropy. The loss obviously changed because the pairwise potentials appear.
Okay, we're seeing different things by the loss.
Yeah.
I meant the loss is just the number of incorrectly recognized symbols. And in this sense, it is the same. The difference is how we define the answers, the predictions.
Yep.
Okay.
Okay, and the key thing in the last plot is that during the first stage, the unary to pairwise potentials ratio grows, since only unary potentials are trained. On the second stage, where we fix the unary and train pairwise, it just gradually declines and stabilizes on the level of the ratio for the best choice of alpha. It's just like when we train in 3 stages, we obtain the same, like in the end of the training, the same optimal ratio as if we pick the best alpha. So it slightly motivates, not slightly, I hope. It motivates the point that the ratio is something which is highly correlated with good results in performance, and which prevents during training to converge properly. Okay. So let me move to the description of models which were considered in this study. First I start with linear chain CRF. Linear chain CRF scalar function has this particular form. The corresponding graphical model has a chain-like structure, which means that during making the scoring on Y, we take into consideration only neighboring hidden variables, yi.
Do you assume some metric assumptions on W?
On W? No.
No.
And consequently, we can define the likelihood and the marginal distribution, like this. And the neat thing here is, as this model has the chain structure, we can infer both partition function and marginals using some product belief propagation, and infer the map and estimate via maximum belief propagation. Consequently, for this model, there are many choices of training objective, since we have like all we needed. So we can consider like a classical one training objective. We train the parameters to obtain the MLE estimate on them, or we can alternatively infer the marginal distribution and pass it to the cross-entropy loss, or we can consider the structured SSYM objective, which intuitively just pick the parameters theta, which minimize the maximal gap between the true prediction and all others with some margin. The margin is denoted by delta theta. In case of sequence tagging task, and in our study, it is quite natural to pick it equal to the Hamming distance, which is just a mean discrepancy of the elements in string on corresponding positions. No questions so far? And now I'm going to discuss Gaussian CRF model. It has like a different nature because we no longer define the scores on the discrete domain, as here is continuous one. It's just this quadratic functional. Scores here is just this stacked vector, where Sij corresponds to the score which is assigned to pixel j if it is labeled I. Like, very complicated. L here is 1, blah blah blah. L is the number of pixels, is a pixel.
Mm-hmm.
The second index is a pixel, the first index is class. M is a number of classes. Okay, the unary potentials have a similar structure, and the pairwise potential in this case is a positive, semi-definite square matrix of size Lm. How we denote it, I'll briefly discuss further. So in this case, as we have a quadratic functional, we can easily obtain optimal scores via the solving of system linear equations. It can be done efficiently via conjugate gradients. And then we can define our marginals on the discrete variables as instant-wise softmax.
How many indices? S.
It just
Okay.
we take all, which corresponds to the pixel j, and take the softmax, and we obtain the distribution of classes for j's pixel. Okay. And consequently, at the evaluation stage, we can make prediction just by
I'm very sure, but S star.
S star. Yes.
What is this? Is it I max of Fs
Yeah.
given x theta?
Yes, in particular, yes.
Mm-hmm.
Because you may think about it as a map on these continuous scores with respect to this score function. And during the evaluation stage, we can make the predictions by taking instance-wise our maximum. We just pick all scores for the G's pixel and take the class which corresponds to the highest score. As during the forward pass, we are in particular solving the system of linear equations. Brute force rollouts through the iterations of solver would be quite inefficient. Luckily, in this case, we can solve linear system in backward pass to obtain the corresponding gradients with respect to parameters u and w. Now I'm going to discuss a particular structure of pairwise potentials in this case. It follows the class-agnostic POTS model. Assume that for each pixel I, we have an embedding, and why it's pack-agnostic or class-agnostic, because this embedding does not depend on a class which is assigned to pixel. It's just like completely indifferent to the class which is assigned to it. So, and the resultant pairwise potential matrix is defined in the following way, because if the classes coincide, we say that the score is 0. If they don't coincide, we say that it's just a dot product of corresponding embeddings. It's just like a classical POTS model. And if we add up lambda e, we ensure that it is positive definite. Thus we can use the conjugate gradient.
But how many classes do you have here?
It's just two classes because we assume like binary symmetration.
Mm-hmm.
And if you have like n classes, you would have like this block form. You have zeros on the diagonal and just the number of classes here, because it's class agnostic. It would be alpha dot alpha transposed, alpha dot alpha a dot alpha dot a transposed, and so on.
Okay.
Okay, as we claim that the relative scaling is the problem here, let us manually ensure that the scaling is proper. So the idea is quite simple. Let us slightly modify the score function. We just scale up the unary potentials, and during the training, we just train like regularly with this score function, and after each epoch, we grid search the optimal alpha via the subset of training. The whole algorithm can be summarized as follows. We just like run the average, do the average, and then grid search the parameter alpha with respect to the loss on the trained subset. Any questions?
But during the epoch,
We do the training with modified score function. With this
yes, but then you modify it again, right?
Yep.
So
We just modify
it
this
may happen that you train your model with one values of alpha and you use it with different values of alpha.
No, we just pick the last epoch value for evaluation.
Mm-hmm.
It's just like
But what is the motivation of constantly changing alpha during training?
because for some models it's not possible to pick a constant alpha. For instance, in case of binary segmentations, it's just like highly unstable. It changes the training.
Okay, but what will happen if you set it to alpha best? You will be able to train such model.
Yes, we would be able to. We always are able, in these particular examples, to train it, but the accuracy is less than in stage 1.
And what parameters do you train here? What are the theta? Is it
theta-
just this embeddings?
No, it's just different for different tasks. For some tasks, you may consider that U is an output of neural network and W is an output of neural network. During the epoch, we train the parameters theta, which are the parameters of neural network, and after that, we perform a grid search with respect to this scaling factor.
Okay.
Okay, here we just like call it online because the alpha changes. So we would like to consider some more like effective way in terms that we don't do grid search after each training epoch. So we have no longer flexibility to. Oops. I should have. Well, you have a question.
Is it true that this alpha grid doesn't imply computational costs, computational costs, because loss computation is really fast?
Yes. Because we don't need to prof through it, you have like some routines in PyTorch like no-grad, like it's very efficient. And we just pick in the subset, not the whole training set in our experience, and that works fine. And I should remark that in some models we can choose the constant factor alpha with such parameterization, and in fact it's just a special case of initialization for the last layer of our unary predictor and the special learning rate for it. So you can consider it's just like the tricky hacks that I mentioned in the beginning of this talk to make it like stage training very efficient. But here it's like quite naturally arises. So let me skip to the next method, which is offline one. We no longer have a flexibility to choose the alpha So we mainly manually do the scaling with alpha. We just renorm our potentials. This norm braces denotes just a mean absolute value of the matrices, and we choose the constant alpha here, and we can, in other way, consider the implicit regularizer version, where we just add up this regularizer to our loss function, and we choose the parameters alpha and lambda on the validation set. Well, the motivation of such manual normalization here, as I said, is that we cannot no longer guarantee that during our iterations, assume there is none denominator here. We can no longer guarantee that our model won't learn to make very big unary potentials and completely forget about the structure term. So if you manually rescale it, it will somehow ensure that the scaling is almost the same during the whole training. In particular, the ratio would stay up to noise the same because we have different norms. Yep.
Why is it good that the ratio is constant? Norm ratio of norms is constant. Why is it good?
Because the claim is that for training such models, there is a good ratio for training them.
And you know this ratio?
No, that's why we are picking it by cross-validation, the parameter alpha. Because it is highly dependent on the task. It's the discrepancy of value is very high from task to task.
Is this an empirical claim about?
Yes, it's a purely empirical claim. But we encountered it multiple times.
Yes, but you mentioned earlier that if you set alpha constant, in
For
many
some
cases,
models, it is possible. But the parameterization is different. In this parameterization, you don't norm your unary potentials.
I see. Okay, got it.
And as you have a flexibility to tune this alpha during the training, you can compensate over unary predictor, which is I'm good and pairwise or not.
Thanks.
So, in actual, it is as follows. So I'm going to briefly discuss the tasks which were considered and the respective architectures for unary and pairwise potentials. First of all, optical character recognition. I've already mentioned that. The goal is to recognize the word given sequence of its images for each letter. As unary predictor, we take the LeNet5-like neural network. As pairwise, it's just the real valued square matrix of size 26. Text chunking, it consists of dividing the sentence into syntactically correlated blocks of consequential words. You can consider an example for the sentence, here equals the current account deficit will narrow to only 1.5 billion in September. It has 8 blocks. And as unary, we take the following architecture. We pass each word through the char level RNN, in particular VLSTM, to obtain some representation of this word. Then we concatenate the final hidden state with the Sen embedding, which is word to back. And we additionally provide it in the dataset with the position tag, which we concatenate to this huge vector and pass it through the fully connected layer to obtain the final unary potentials. For pairwise one, we just equally to the optical character recognition case pick the real value matrix squared of size which corresponds to the number of possible tags. And binary segmentation. The goal is to distinguish the pixels in background and foreground. And we pick that little pony data set, well, it's not in there, but it's Weissman horses. We have unary and pairwise potentials parameterized by UNet-like fully convolutional neural networks.
One question, is it known to?
No, it's not.
Because one extra leg.
Some zebras are discriminated, perhaps. So that's are the architectures and the tasks. So are there any questions? Everybody knows what unit is, yes? Okay. And let me move to results. A huge table. We can see that the stage procedure is always superior to the joint one. The numbers tell us. And our proposed online and offline regularizer version are achieving the same up-to-noise performance to the stage training, but it is necessary to say that the hyperparameters tuning is less ambiguous, and it's 2 to 3 times more faster training than the stage one.
And what's better, online or offline?
Online.
Online.
In terms of accuracy, yes. In terms of efficiency, offline, since we don't perform grid search of the leads.
Okay, and offline or offline with the regularizer?
Offline.
Offline. So when you fix the ratio?
Yep.
This can be regarded to some kind of hard regularizer, right?
Yes, it's a hard regularizer, yes.
So and the last column converges to the previous column if lambda goes to infinity, I guess. Because then the soft regularizer becomes
When
harder.
sufficiently large, yes.
Mm-hmm. Interesting.
Okay, and so if nobody has questions, I would like to conclude.
The difference between the two columns is not statistically significant.
It depends on how you measure statistical significance, because
It's one deviation away.
it's uniformly better
Okay, what's your
on a
question?
large number of problems.
Artem, do you claim, we are not claiming that we are better than the stage one. We just
No,
say
no,
that.
We're comparing two last columns.
Two last columns, yeah,
offline
they're quite-
regularization.
And the last column is uniformly worse than the previous slide. And if it's so, then we can prove it and derive some statistical significance tests.
Oh yeah, like I read. Okay, and but the interesting thing that offline regularizer is just like an implicit way to constrain your unary potentials. But in the pure offline, you need to manually like rescale them. Any questions? So let me conclude. We conjectured that the scaling is the main reason to joint train to fail. We proposed offline and online scaling algorithms and demonstrated their efficiency on 3 different tasks. I'm not sure if it's like a good way to say thank you for your attention, and I can answer additional questions.
Well, okay, let us first thank the speaker. So, any questions?
Can we use this technique in some way to tune the scaling factor in alpha?
Well, I'm not completely familiar with it, and I'm not completely sure, but perhaps yes. I should try.
I don't think so, because in elbow it's a linear parameter in the objective itself, and here this parameter is hidden inside the objective. So like here, like both extremes are obviously bad from objective point of view.
Can you please return to the table?
To the table.
Yeah. So you mentioned that for each problem there's a optimal value of alpha, right?
Yeah.
More or less.
More or less for each method, yes.
Is it the same for
No,
different?
no, for different losses it's not. And in particular, the probabilistic losses are like quite good because we have this natural normalization in them, but the structured SVM is not like them. It's like a completely distinct one because we have just the difference between scores, and we do not have this natural normalization which is delivered by the partition constant.
Okay, and what about the situation when the tasks are different but the loss is the same? What about optimal values of alpha? Are they different?
They're different. Like discrepancy is quite significant.
Haven't you explored some kind of dependence of optimal value of alpha and say the number of objects within your graphical model, something like that?
Well,
But for binary segmentation you have many pixels and in OCR you have a
it is dependent, yes. But we just didn't conduct it like a special case of.
So do you have any intuition?
Yeah, less. Well, yes, because if you have like many pairwise potentials, many of them, you should like have, I guess.
Should you decrease its
You should you should increase the
strength of unary potentials.
Wait. You should increase, yes, the alpha.
And alpha is the strength of unary potentials.
Yep.
Sounds
Because-
reasonable. Otherwise the pairwise potentials will dominate.
Yep. And it is like proven by the choice of best alpha for these cases. Just like in this case, you have like a very huge pairwise potential matrix, and the value of alpha is like 10 or 12. And in the OCR case, you have just 1/2 or 1/3, some kind like that.
Excuse me, one question. Does the number of pairwise potentials depends correctly on the number of pixels or not?
Well, the thing here is, yes, but for that model which I presented, this Gaussian CRF, you can't make a complete correspondence between the score function and the geographical model, because it's not equivalent to the dense CRF model where you like have all pixels connected to all others. But in some sense it is, because when you have here you just like have a dot product for all pixel to label embeddings. So in some sense you are taking into consideration that all pixels depend on all others, but not explicitly if you define your score functions on the discrete domain on the vertices explicitly. Do I sound like...
Well, so the question is, the scale of pairwise term is linear or not?
Well,
Of number of pixels or
it's not linear. It's not linear because it is seen from our experience that it's not. But I'm not completely sure that it's quadratic.
Okay.
Actually, the number of pairwise potentials should be equal to the number of edges in the graphical model.
Yeah,
And
but
the number
I
of edges
said
grows
that,
linearly.
yes, but I said that this score function has no implicit representations in terms of graphical model. Because you define your scores not like in natural way on discrete domain on the on your hidden variables. You define it on the scores for each hidden variable to be assigned with the label. It's in some sense it is close to the dense CRF model, but it is directly not. It doesn't induce like a correct graphical model on a discrete domain. Like a correct in terms it is equal to dense CRF.
Okay. So any more questions? If no, let us thank the speaker again for its